The lecture 5 per recording is about the semantics of imperative statements. So first of all, let's clarify what we mean by imperative statements. The most essential aspect is assignment. Assignment turns a language into unleashes its capability of telling the computer to do things, right? So that's why we call it imperative. It's like do this, do that. We're going to see several other paradigms which are different. For instance, Prolog, of which we have sampled a bit, has a different way, right? It's based on logical inferences, so it's a declarative language. We declare what we want to compute, and we let the computer figure out how to compute it. So the important aspect here is assignment. It's the most most important aspect of imperative programming, and in order to administer the assignment, we need means of aggregations or aggregation of compounding statements. So these would be the iteration statements, while loops, for loops, do while loops. Actually, the while loops are sufficient, right? And we will only implement those. We have already sort of know that for loops and do while loops can be implemented as syntactic sugar in terms of while loops. And we need decision statements. And important aspects, but not essential, are the implementation of procedures and recursion. All right, and we're going to discuss this at some point later. They are not really exclusive to imperative programming. The execution model of imperative programs is based on a notion of state, and every action of the program takes the machine from the current state to the next state. The essential aspect that changes the state is assignment, because we are changing the values of the variables, and those are the main component of the state. And computation, by computation we mean the sequence of states that a program goes through. So we're going to take as a case study Python, and we're going to study Python in detail later in the live lecture. So let's see examples of imperative statements. You can see that we have a lot of assignments there, and then we have a while loop, right, which has two components, the while condition and the while body, and then we have an if statement which have an if condition, a then branch, and an else branch. So with this we have the main components of an imperative language. If we have only these, we can perform any computation. We are already in the realm of Turing completeness. You probably know already that by Turing complete we mean the full power of computation, right? Everything that can be computed in the world can be computed by a Turing machine. So as soon as we are Turing equivalent, we have the full power of computation, right? With a language like this, having only assignment, while loops, and if statements with else, and possibly the else branch may be missing, we already have Turing completeness. So we're going to try to define the semantics of such a language, right? Very simple, nevertheless Turing complete. All right, so this pertains to Python. We're going to understand later how Python works. Let's look at what semantics means. So semantics is a branch of mathematics, and in general is that branch that assigns a mathematical description of the execution model of a language to every program of that language. Essentially, it's a translation mechanism, right? Because we assign an object, but that object has to be described mathematically, and in mathematics we also deal with a language. It may not be apparent, but when you say that X is the set made up of the symbol A and then X union Y, all right, these are variables of the language, these are operators of the language, this is a constructor of the language, and so on, right? So this essentially is a language, and what we do is translate from the base programming language that we have chosen to give semantics to into a mathematical language. We operate under the assumption that we know the description language. So if it is the case that our semantics is a mathematical one, we assume that we know mathematics. So that will be the description language. And by giving semantics, we essentially explain the language in a very precise manner, right? You may think that you can pick a programming book to learn a new language. Guess what? Experienced programmers and mathematicians will pick a book that contains a description of semantics and learn the language much faster. And would be good if you can acquire that skill. Now, each construct of the language must be described somehow, and in doing that, we're going to go by the grammar. Essentially, the grammar that describes the language. Now, since we are in the business of defining a process of translation, right? We can even generalize that, and we can say that any translation of the new language into an already known language can be called semantics. So a compiler is a means of giving semantics to a language, and actually this is the approach that we're going to take today. We're going to build a small compiler for the language that we have discussed. So in order to understand the structure of the language, because we have to go hierarchically by the structure, we have to start with the grammar. So the grammar of our language is the grammar of statements, all right, and it has the following. It has assignments, which have this format. It has if statements with else branches, right? So the first kind of else if statement has an else branch. The second kind of if statement does not have an else branch, right? Notice that for the branches of the if, the braces are compulsory. So we're taking an approach similar to Perl, the language Perl. We are doing this because it's easier to implement such a language in Prolog. So we are complying with some Prolog constraints here. We have while statements of this format. Notice the keyword do in between the expression and the block. And again, the braces are compulsory. We have blocks. So these are blocks, statements enclosed in braces, and we have sequences of statements separated by a semicolon, and occasionally we may want to terminate statements by a semicolon the way that C does, and we might have this kind of statements terminated by a semicolon. Now we have two kinds of expressions, Boolean expressions and arithmetic expressions. So Boolean expressions are defined in the usual way, having expressions joined by the relational operators, right? Smaller than or equal, equals, right? Logical equality, then logical disequality, greater, or equal. Yeah, and the expressions are the same as before. We have already given a grammar for expressions, and we're gonna stick to that one. And what are we going to use as a target? What is the known language that we can use to assign meaning to the new language? The new language was the one whose grammar you saw on the previous slide, and the known language is the vanilla assembly language, which we have discussed over several lectures. We consider it to be known. All right, and let us discuss a few elements of this language. We're not after implementing the most efficient val code. So that's one important thing that you have to remember. We're after readable and clear implementation that would actually showcase the process of assigning semantics to a language. We're going to need a stack for evaluating expressions, right? And actually the processor offers always a stack. It has a register that acts as the top of the stack. The stack grows downwards. You might know this already. So since our memory has only 10,000 elements, we're going to initialize it at this value. and we're going to allow it to grow downwards as the stack of any processor would do. So every push is going to be implemented in this way. We decrease the stack pointer to make room into the stack, and then at the newly created stack location we can store a register. And notice that this assignment obeys the rules of val assignments, right? So since this is already a memory reference, this has to be a register. We cannot transfer memory to memory. And pop will be the reverse. So we load a register from the top of the stack location, which is given by this expression, right? This is the one that gives the top of the stack, and then we remove, right? We essentially destroy that location by increasing the register. So we're going to use this push and pop operations very often. Now, before we go to defining the compiler, let's see the world of semantics. What does it offer us? In fact, there are quite a few types of semantics. These are the most well-known ones. There is a type of semantics called operational, and actually there's two subtypes there, small step and big step. There's one type called denotational, which translates language fragments into lambda calculus formulas, right? So remember that scheme is essentially a representation of the lambda calculus. So it's like translating from our language that we have defined, the one for which we have given a grammar a couple of slides ago. So translating from that language into scheme, that would be denotational semantics. Operational performs a translation from the given language into a transition system. And is essentially a way of defining an interpreter for a language, right? So if you want to define an interpreter, it's usually the simplest kind of semantics that one can get, small step semantics. It defines an interpreter, and if you want to write an interpreter for a given language, you go and look for the operational semantics that is published somewhere. There is something called collecting semantics, which is very useful in program analysis. So it is the basis for performing program analysis. There is another kind of semantics called axiomatic semantics, which is the basis for program verification. You might have heard of for logic, or you might hear of for logic if you go into 3234. This module 3234 is called formal logic, and part of it will introduce for logic, which is a logic for program verification. It's a logic for reasoning about programs. And we have various combinations of the above, and we also have a lot of non-standard approaches. We will take one today because we feel that, or I feel that this is the best way of explaining how programs are eventually executed on a machine. So the semantics of our toy language is going to be expressed as reasoning rules, all right, but by assigning to every program fragment a val fragment. The context, remember that in a rule, right, we essentially have a big line with premises and conclusion. And all the premises and conclusions are judgments. Judgments have context and the judgment, the proper judgment, right? And we say that if this holds, or if all the premises hold, then the conclusion in context C, judgment J holds, must be true. All right, so in this case, the context that you see here is an environment which represents a mapping from variables to their addresses. variables to their addresses. And we're going to learn how to give addresses to variables dynamically. That's going to happen later. Right? We also assume that we can generate new labels on the fly. Again, that's going to happen later. So whenever we write a label, and wherever we write an address, we're going to assume that it's a fresh one that can be generated dynamically on the fly. And we're going to see later that this process is actually quite easy to solve. So here is the semantics. These are the rules. All right, we have a number of rules which are called base rules. They do not have premises, so they are necessarily true all the time. Right, so the code, the semantics of a constant. Right, so constants are expressions, and expressions are part of the language. So one of the most basic elements of a program is a constant. Okay? So in any context, curly E, the semantics of K, which we denote by these double square brackets, that's the semantics of K, is equal to, and what do we do? What do? We put here a piece of code that pushes K on the stack. Okay? So that's a very interesting approach, right? Every time we see a constant, we push it on the stack. Okay? Every time we see a variable, we actually do the same thing. Problem is that we can't do it in one step because we would have two memory references. So what we do is we take the memory reference, and notice how we denote the memory reference. V is the name of the variable, and environment applied to name V, to the string V, right, is an integer representing the address of that variable, right? It's a 4-byte area of storage that is reserved for holding the value of that variable. So this is the address, and the value at that address is loaded into ECX and further pushed on the stack. So essentially, whenever we have a value, be it a constant or a variable, we push that value on the stack. This is what the first two rules are saying. That's the semantics of these basic program elements. Now, let's say we have a more complex operation. We have an operation that is of the form expression1 operator, sum operator, maybe plus or minus or star or division or modulo. So there's a second operand called E2. So the semantics of this, right? Well, we can only compute it if we already know the semantics of E1 and the semantics of E2, right? So the premises are, let us assume that the semantics of E1 is C1 and the semantics of E2 is C2. In other words, let us assume that the code representing the expression E1 is C1 and the code representing the expression E2 is C2, right? And then we also assume that the operator circle plus is generic but is one of these set, okay? And then the entire code for E1 operator E2 is this one given here, right? So first we put the code corresponding to E1, then we put the code corresponding to E2. Now what happens when we do that? Well, C1, after the execution of C1, the result of E1 is going to be on the stack. After the execution of C2, the result of E2 is going to be on the stack on top of C1. So then what can we do? Well, since we know the results, how to retrieve the results of the two sub-expressions, we perform two pops. We have two pops here, and then we have the results of E1 and E2 in ECX and EAX respectively, and we can perform this operation to compute the result of the entire expression. Okay? And then we comply with the previously established convention. The result of every expression is on the stack. So the result of the current expression, the one that we have just we are about to compute here, we put it back on the stack by pushing it, right? So this is the semantics of this guy, right? You can regard these premises as, let me compute the semantics of E1 recursively compute the semantics of E1 and let that result be C1. Let me compute recursively the result of the semantics of E2 and let that result be C2. And then now the semantics of E1 operator E2 is the code for C1, the code for E1, followed by the code for E2, followed by this code. And it can be easily seen that if we execute this entire code, right, starting from C1 and ending with this instruction, what we end up having is the result of this entire expression at the top of the stack. Okay, so this is the convention. Whatever expression we have, after executing the code that represents its semantics, the result of that expression is on the top of the stack. So now, having handled expressions, we can do assignments. Okay? So when we look at this assignment, its semantics depends on the fact that we already know the semantics of the expression E, right? So this is an assignment of the form variable is assigned expression, and we recursively compute the semantics of the expression E, let that result be C, and then what code do we have here? Well, we have the code for the expression E, and we know that after executing this one, the result of E is going to be at the top of the stack. So what do? We pop it, and we transfer it into the memory location corresponding to V, the variable. This is a name, right? A string representing the variable name. This expression gives us the address, and we're going to discuss later how this environment is computed. But EV gives us the address, gives us a unique number, right, representing a 4-byte location where we can store the value of this variable. So then what should we do? We compute E, we have the result of E at the top of the stack, we should transfer the top of the stack into the location of V, right? This is what these two instructions are doing. Pop and store into location corresponding to V. So very simple, right? It's very clear now that the execution is proceeding as expected. Now let's look at the if statement. The if statement that has a else branch. So an if statement has the format, right? If E1 relational operator comparison, right? E2, then statement 1 else statement 2. So what do? We are recursively computing the code for E1, right? The semantics of E1, recursively computing the semantics of E2, recursively computing the semantics of S1, recursively computing the semantics of S2. We're assuming that the circle plus is one of these operators. And then what should you do? Well, of course, we have to compute E1 and E2 first. So we put the code for C1 and the code for C2, right? And then we know that after C1, the result of E1 is on the stack. We execute C2. The result of C2 is going to be pushed on the stack on top of result for C1. So now, if we pop 2 elements from the stack, we're going to have the results of C1, of E1 and E2. So all we need is to perform the comparison, and then we use this variable placeholder, right? This label placeholder. This is a label. Every time we generate a new instance of this entire code, we're going to have to generate a new name for this variable, and we'll see how that can happen, right? So if this is true, right, we have to jump to the then branch. which you can see is here, right? Otherwise, we continue on, and we should be executing the else branch. So you see the code for the else branch, which we have computed here, we place it right after the if, and this is going to be executed. This is going to be executed when the condition here is false, because otherwise, if the condition is true, we perform the jump. And we have performed this kind of translation before. We have seen it before, right? So at the end of the else, what we do is we perform a jump that skips the then, the translation of the then branch, so it goes to the end of the if, right here. If the jump is performed, then we jump here, and here we have the code for the then branch, all right, and then execution is exactly as expected. All right, so this entire piece of code represents the semantics of this code pattern. And notice here that S1 and S2, they're generic, right? They may have as many statements as we want, and we can essentially, the semantics is this double square brackets, and this is essentially like a function that can be called recursive. Okay. The semantics of the if without an else branch is very similar, so that we're going to leave as an exercise. Let's see the semantics of the while statement. All right, again, this is the format. So we're going to have while, we're going to have some Boolean expression consisting of some circle plus operator, which is generic, is one of these. And we also have E1 and E2, which are the sides, the arithmetic expressions on the sides of the Boolean expression. And if this is true, then we keep repeating this statement S, which we should put in braces. So we are not very faithful to the grammar that we have originally discussed. This is actually a typo. Imagine that there are braces around S. So how do we translate this? Well, again, recursively, we assume that we have computed the semantics of E1, and that's C1, and we have computed the semantics of E2, and that's C2, and we have computed the semantics of S, and that's C3. And we're going to organize the code in this way. We're going to have a label here to allow for repetition. We're going to have the code for C1, the code for C2. After execution of C1 and C2, their results, the results of E1 and E2 are going to be at the top of the stack, both of them. So we have to pop two elements and essentially retrieve them. So then we can perform this operation. And if this is true, we go to this label that executes the while body, which you see placed here. Right? If we haven't performed this jump, if this is false and we do not perform this jump, we're going to get to execute this unconditional jump, which takes us to the end of the while loop. Now, after the execution of the loop's body of C3, C3 here, remember, is the code representing S. So after the execution of C3, we have this unconditional jump taking us to the top of the while loop, allowing the repetition of the entire loop. So again, this entire code represents this program fragment, right, where E1 and E2 and S are generic program fragments, right? Of course, E1 and E2 have to be expressions, and S is a generic statement. And to find out the semantics of these three guys, we can recursively invoke the compiler. We can recursively invoke the semantics computation, right? And this will produce results as expected. So what happens now? We have these rules. Of course, we haven't written all the rules. There's the rule for an if with a single, with just a then. That's missing, but it's very easy to write. Okay. And we have not given the rules for sequence, right? And for for block. But those again are very easy to write. Just to give you a quick idea, right? If we have that in E, the semantics of S1 is C1, and also in E, the semantics of S2 is code 2, then in E, in E curly E, right, the semantics of S1 followed by S2 is going to be precisely C1, C2, right? So I write the code for S1, then I follow the code for S2, and that's easy, right? And for the curly brace, we just do the same. Curly brace just means nothing. It's just a way of grouping statements. So remember, rules are very easy to translate into Prolog rules, and that would lead us to a very simple compiler that we can write in Prolog. All these rules will follow precisely the rules given before in the previous slides. So what do we have here? We have the program fragment that had this first argument. We have the environment, and we're going to play a trick here because we don't know what variables we have in the program yet. We could do a two-step processing. First of all, find out what are the variables, and then perform the translation, and then the environment would be constant. But we want to be a little bit more efficient. So the environment will grow every time we encounter a variable. The environment is going to essentially be a list where we can map variables into their values, and we're going to map variables into values by occupying the memory from 0, right, from 0 and to higher values. So we need to keep track of which is the first unallocated value, and that will happen here in this arguments t in, t out, right? So looking at the second rule, where it's more apparent what the arguments mean, every time we add a variable, we're going to add the variable to the environment. So the rule receives an environment, and when we finish the rule as output, we have a larger environment where the new variable has been added. And because the new variable has been added, right, let's say that this was the top of the memory in, right, but we have allocated an extra variable, so we're going to have the top of the memory out that has increased by 4 bytes. This is precisely what is going to happen because this is the rule that deals with the variable. So let's follow the rules. So whenever we compile a constant, right, we have to check that this is indeed a constant. So the program has to check. This is the side condition being implemented. If you go back to the rule, you will remember that you will see that there's a side rule saying that k has to be a constant. And then we generate the output. We write it directly, right? And the output was exactly the one given in the rule, this one, right, which pushes the value k on the stack, right? And we want to be quite verbose, so we're going to add a C comment reminding us that this is a push. What happens in the case of a variable? We check there is a variable. This is again the side condition. And then what we want to do is dynamically augment the environment. So we check whether this variable has already been assigned an address in the current environment. And this is the Prolog's if statement, right? And this is the then branch, and this is going to be the else branch. The then branch is the one where the variable already exists. If the variable already exists, there's nothing to change. The output is the same as the input. The environment remains the same. The variable is already there. And the top of memory at the output is the same as the one at the input. However, if the variable does not exist yet. All right. We want to add it. So how do we add it? First of all, we allocate memory, meaning that the top of the memory is going to be the top of the memory at input plus 4. The new top of the memory will have 4 extra bytes allocated to the given variable. And then this variable, being mapped to this address, is added to the output. And this is an augmentation, right? Meaning that all the old variables with all their mappings are still part of the environment. Okay? All right. Now, if this V is already mapped, this is where the address of V resides, and we make it so that even on this branch, the same prolog variable holds the mapping for V. We make the address equal to T in, so this will become the mapping for V. So in the code that we generate for our variable, we can use the address, right, as an index to the memory. Notice here that we're essentially generating a val line, right, saying that ECX is assigned, right, the contents of the memory location given by address. We close the square bracket, and then we push that ECX. All right. So this is the rule for the variable, right? The value of a variable has to be pushed in memory. Now, what's next? Well, next we have the rule for compound expressions, right? This is a expression A and expression B joined by the operator O, where the operator O is one of plus, minus, multiplication or division. So what do? Exactly as in the rule, right? This appeared on top of the line. So we recursively call the compiler for A. All right? And then we recursively call the compiler for B. And one important thing whenever we have these the sequence of recursive calls is the threading that we have to do, right? So you see the input that comes from here is threaded into the first recursive call, comes out here, is threaded into the second recursive call, comes out here, and goes back into the output of the whole predicate, right? So input goes to the input of recursive call. That recursive call provides an output which is fed further into the input of the next recursive call. That provides an output, and that output eventually is pushed into the output of the entire recursive call. The same happens with the top of the memory. So T in, let's use a different color here. So T in is threaded into the first recursive call. The output of the first recursive call is threaded into the input of the second recursive call, and the output of the second recursive call is threaded into the output of the entire predicate. Okay? And after we have done that, what do we have? Well, we have code, right? So these instructions have written their code. Notice that we, in our predicates, in our rules, we write our code out directly, right? So the code does not come back as an argument. It's already written in the standard output. And what do we know about the values of A and B? Right? According to that code that has been already written out, it's in the top of the stack. Right? So this code will put the result of A on top of the stack, and this code will put the result of B on top of the stack, right, after the result for A. So now the results of A and B are both in the stack. So we can pop them. We first pop the result of B, then we pop the result of A, then we generate code that performs the operation, right? So the result will be in EAX, and then we need to say star equal. So notice that we write the O, which is the operator. O will be either plus or minus or star or division, right? So this O will be immediately followed by the equal sign in the output, right? So what you're going to read in the output is EAX, let's say plus equal ECX, and thus performing the operation, assuming that this O was plus. And then we have a new expression, a result of a new expression. The convention is that the result of every expression is pushed on the stack, so this is what we do here. We generate a val statement that pushes the result of the previous operation on the stack. Okay, and we also generate, to be verbose, we also generate automatically a comment that explains what we are doing there. So this is it about expressions. We have handled constants, variables, and compound expressions. So now we can move on to statements. The first kind of statement we handle is assignment, right? And now we need an extra set of inputs and outputs. We need labels. We need a set of input and output labels, so we can handle jumps correctly. Remember that for each piece of code we actually have to generate new label names. So the same thing continues. This statement will not generate any labels, so the input labels is the same as the output labels. There's no need to process them in any specific way. However, the rest of inputs and outputs have to be handled, because the input that comes here has to be threaded into the recursive call. The recursive call generates this output. This output has to be checked, because here we have a new variable, which is potentially new. It's a variable that may not have seen before, So then we have to check whether it exists. If it exists, very well, this is what we do. We just say that this auxiliary environment is the one that we use for output, and this auxiliary top of memory is the one that we use for output as well, right? That's in the case when the variable has already been seen before and it already exists in the environment. However, if it isn't, then we have to create space. So this top of memory has to be furthered, right? Has to be enlarged by 4. So this will be the new top of memory, and we have to add this new mapping between this variable and its new address. We have just allocated this address for that variable, and right, this mapping has to be placed in the output environment together with all the old mappings. We can't forget the old mappings. And we use this ADDR as the address of the new variable. So on this branch we make ADDR equal to T auxiliary. On this branch, on the true branch, we make this ADDR to be the address of V. And now we can generate code. So what do we do for this assignment? Well, remember, we have just generated the code for E. E is a possibly compound expression. So as we perform this compilation, the code has already been written out, and according to that code, the result of E is at the top of the stack. So we pop the value at the top of the stack into ECX, and that's the value of E. Alright, and we write into the memory address corresponding to the variable V, into this address, we write the value of E, essentially completing the assignment. Okay, the blue area of code shows how we can run this rule for just one assignment. All right, so this assignment has, because we already have the code for expressions, right, we can actually test our latest rule. So we have a little expression here, and we have an assignment of this to x. So what's going to happen is the following, right? This is the query, and this is the output that is written out, and this is the answer. So all the right statements are going to produce this part that I am now highlighting in blue, right? All these right statements, and including the right statements that we have seen on the previous slides, are going to generate this output. So notice the following, right? We have an address for y, which is 0. Y is the first variable encountered. We start the allocation from 0. So 0 will be the mapping of y, right? And what do? Whenever we see this y here, we are pushing y on the stack. And notice the fact that we're adding these comments to explain what we're doing. They're automatically generated. Then we push 2. The second line will push 2, right? Because 2 is here. Then what we do is we pop 2 and y, and we perform the addition. And it looks a bit stupid because it's inefficient, right? We do a push of 2 values, then immediately we do a pop of 2 values. Why can't we just load the 2 values into registers and perform the operation? The problem is that it's not so simple to keep track. If we try to do that, it's possible, and compilers will do that, especially when they optimize code, but it's not so easy to keep track of where our partial results are if we use registers, and the code will be much less readable and much less easy to understand. We are in a quest for finding simplicity in this process, and this is the simplest way in which we can define a compiler. We can write a compiler. So now EAX contains the result of y plus 2, and as we established, we want to push this on the stack, so that's because that's where the result of an expression resides. So from here up to here, we have just compiled the expression y plus 2. And now we can do the result of this rule. This is what this rule does. It generates this output. This output is what you see as these 2 lines highlighted in pink. Okay? So what we're going to do, we're going to see ECX, right? So this ECX is assigned this guy. So you see it here. Right? So essentially we're popping from memory, and ESP plus equal 4, we're popping, right? And then we're writing into the memory of X. So now X, you will notice probably that this part right here has mapped X into a new address. So X will be mapped, since Y is already mapped at 0, Y actually occupies the memory addresses 0, 1, 2, 3, right? 4 bytes. So X will be mapped into 4 and will occupy addresses 4, 5, 6, 7. So what we're going to do is, into the memory address 4, we're going to write ECX, effectively placing the value of the expression into the location that stores the value of X. Okay, and this is the output that you can see here, right? So this guy, which you see here, the 4, which is this guy, will be the 4, and then the rest of it, which you see here, starting with the closed bracket up to ECX. And then notice that we also generate this comment, which is here, right? We're explaining what we're doing. We're popping X. Okay, so this is how the rule for assignment works. Similarly, we have a rule for the if statement. So if you look carefully at the rule that we have given here, right? So on this slide, we have given this code, right? And what you're going to see is recursive calls for all these guys with threaded inputs and outputs, and then we try to generate this code. Okay, so this is the if. So we're going to have four recursive calls. 1, so 1, 2, 3, and 4. Okay, and we are calling all these things at the points where actually the output needs to be generated. Okay, and in between the recursive calls, we are generating all the other pieces of code exactly as explained in the rule. Right, and we put a comment here to explain what we're doing. We're putting the code for expression 1, expression 2, right? We're popping the results from the stack, right? We're performing the operation. Okay. So comparison between EAX, this is the comparison operator, and ECX, and we generate a goto, and then we have the ln label, and we're going to need to generate new labels all the time, right? So this ln will have a number here, and this number needs to be fresh. So how do we do that? We use this ln lout, right? So ln is the first number for a label that we haven't used, so we're going to be using it here, and then we're going to output in lout the first number of a label that hasn't been used, so it can be passed on to the next threaded call, right? So that each call generates fresh variables. And by fresh we mean we use this name, these names, with a number, right? ln div 1, ln div 2, ln div 3, l then 1, l then 2, l then 3, and so on, right? Every time they have to be completely new. All right. So this is an example of calling the if rule in the simplest possible way. So we have a very simple expression. We have a simple assignment here and a simple assignment here. We already know that we can compute assignments, right? So what happens is that we have the compilation of x and y, which are just pushes because x and y are very simple. We have the pop, which is done by the if statement. We have the comparison. Notice that a new label has been generated with the suffix 0, right? This 0 makes them fresh, right? Not used before. Then we have to compile the else branch, right? So what we do is to compile that assignment. This is the code for the else branch, and this is the code for the then branch, and these are the labels that have been generated by the if rule. Okay, and that's about it, right? So this is this code, this val code, is the compilation of this if statement of the language. And similarly for while. All right, so going back, we're essentially implementing this code. We're going to have 3, so 1, 2, and 3 recursive calls, right, and placed exactly in those places. So we follow precisely what we see in that rule, right? So the first recursive call, the second recursive call, we retrieve the two results from the stack, we compare them, right? And if true, we go to this label, right? Then we have these labels here. Right? So then we have the compilation of the loops body, and we have the several, just the labels. We have several labels to generate to make the code repeat and to allow the exit from the loop. This is an example, right? If we call this rule, again with a very simple body, right, you're going to see that the comparison is here, right? So this is x less than y, and the loop body is here, right? And here in pink you have the retrieval and comparison, and then the labels of the while statement, and here again we have jumps and labels that allow repetition and exit from the loop. So with all these elements, now we can proceed to we have several rules. We've discussed them, right? So we have a rule for sequencing. We have a rule for S with a semicolon as a terminator, and we have the block rule, right? The block rule simply removes the block, because if we have a sequence of statements, it can be further handled by this rule. And having all these rules, we can endeavor to compile complete programs. What else do we need? Right? Well, we need something that will perform all the declarations and also generate a main that can test our program, right? So we have a main compile predicate here that will use the compilation predicate inside here, and we'll put declarations, right? So you can see the declarations for the registers here. You can see the inclusion of stdio.h. You can see declaration of memory. You can see the declaration of the exec function, right? Then the code for our toy program will come. Remember that we might have the last instruction here. The last thing that this generates is a label. So we want to always be on the safe side and put an empty block to serve as a holder for the last label, right? If we don't have a last label, then this still does not constitute an error, so it's fine. And then we're going to generate a main, and in that main we're going to generate printing statements for all the variables that appear in the program, right? We don't have an output instruction in val. The only thing we can do is print the values of the variables at the end of the program, so we're going to generate printing statements, right? This is done by the by this output vars predicate. It will generate printf statements for every single variable in the program, and now we have a complete program. So what can we do? We can take a full-fledged example. This is an example that computes the greatest common divisor of two numbers, which we input here as constants, 144 and 60, and you will shortly recognize this program as the one that computes the greatest common divisor. And we compile this program, and what we need to see is a full C program in the output. So this is what the output is going to be, right? So notice that it's a full program, and actually I can demonstrate how it works by going to Prolog. I have already loaded the program, so all I need to do is cut and paste, Control C. I can go here, do a Control V, and then type enter, and you can see this program, which I can cut and paste. So let me try. I can't cut and paste in one go. Let me try and cut and paste in two parts. So I'm going to cut and paste up to this if condition. Control C, and I'm going to go here. I'm going to open a new file, which I'm going to call test.c. Control V. I go here again, and I'm going to copy some more. Control C again, Control V, and finally the main. Alright, so Control C, Control V. Notice that we actually do have a final label, so this empty block here was necessary. I'm going to save it, Control S, and then I can start a compile window. Which apparently takes quite some time. So you can see the test.c that was there saved, and now I can do gcc -o test.exe test.c, and it compiles without error, and I can run test, and I'm gonna get the values x and y being equal to 12, which are the both of them are the greatest common divisor of the initial values. What were they? 144 and 60. Okay, so what we did is we took this program, we compile it. This was the result. All right, this was the result, which we have cut and paste from the output into a text editor. We saved it into a C file. We compiled it and ran it, and the program automatically prints the values of the variables. These are the printing statements, and the result was 12. So now you can look carefully at the program and identify what are the elements of the original program that correspond to which elements of the val program. Notice that it's a correct restricted val program, right? And you can test it, take it and test it. I'm going to upload the source, of course, and play with it for any other programs that you would like. Check the output, compile the programs, and try to understand how it works, right? This essentially is the process of compiling any kind of language into assembly language. Remember that that's what the processor executes in the end. Right, machine language, assembly language, all the fancy constructs, all the objects, all the functions, all the higher order functions. In the end, they boil down to executing some machine instructions, and the process of translation is one that has to be feasible. You have to come up with one that works. Okay, so this is pretty much it for today. One thing that we have learned that is very important and is going to come back again as a theme is the concept of compositionality. Small components are combined together to form bigger components, and the bigger components can be further combined in the same way. It's a concept that is similar to the one that allows Lego bricks to be combined together, right? And coming up with compositional architectures takes a certain level of skill, so do not neglect it. It's not straightforward to produce, right? This is the Lego paradigm, right? It has studs and hollows, and the studs fit into the hollows, and then what you get is an object which at its edges, right, at its edges has more studs and hollows. So they can be further combined with other components. This is a new entity obtained by combining smaller entities, and it's still combinable further because it has this structure. Okay, so remember, this is what we learned today. The semantics of a language is a description of the execution model in a language that we supposedly already know, and we showcase this by building a small compiler that generates val code. Val is considered known. The programming language that we have devised is considered unknown, and by looking at how the compilation works, we're supposed to understand the language, the new language. All right, and compilation is an instance of giving a semantics to a language. Many other semantics exist. In creating semantics, we need a compositional structure, right? And one aspect of compositionality was pushing the result of every expression on the stack, right? So then that was sort of the stud, and the hollow was popping it. So two independent pieces of code, two independent fragments, could easily communicate via the stack, get their arguments from the stack, because that's where the previous pieces of code compiling the sides of the expression have put the partial results. Also notice that Prolog is perfectly equipped for writing toy compilers, right? I would challenge you to write a toy compiler in any other language. Take the language that we have implemented today and take another implementation language other than Prolog. Take C or Java or Camel or Haskell or anything you want, and come up with a program that is as concise, with a compiler that is as concise and as this one. Yeah, I challenge you to do that. So this is it for today. See you in the live lecture on Friday. Hopefully you enjoyed this presentation.